Well, hello and welcome you too. Mr. Robinson back here with yet another brand new, exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Okay, step on inside, and for the Integrated Math 2 core, in the Big Ideas Math textbook, we are now on section 1.5, Radicals and Rational Exponents. This is section 5 of 6 from chapter 1. Section 6, with my next video coming up, should be on exponential functions, and we'll see that. So we are going to be doing, for this one here, a lecture overview on radical and rational exponents, as well as a problem set. I do not remember how many problems there are. It'll pop up soon enough when we find that actual set. We are going to be talking about how to find nth roots, and being any number, really positive integers, whole numbers, first root, second, I guess not first root, second root, third root, fourth root, things like that. And evaluate expressions with rational exponents, a rational number being a number expressed by a fraction of two integers, such as A over B. So think of fractions, exponents with fractions, fractional exponents, and solve real-life problems involving rational exponents. Okay, so let's get into the nitty-gritty of that. You know, we started talking about exponents, exponential properties in 1.4 in the last video. And we made mention of, obviously, positive exponents being the number of times you multiply something. The zero exponent is 1, and negative exponents are how many times you divide something. Well, a rational exponent, what if there's a fraction inside the exponent, like to the 1/2 power, something like that? That is equivalent to a root, to a radical of some form. And, you know, I kind of sight read this stuff, so I don't exactly know how they're going to talk about it. Let's take a look. You can extend the concept of square roots to roots of other types, because 2 cubed is 8, and 3 is the fourth root of 81, because 3 to the fourth is 81. They're, okay, so that's what they just refer to roots, right? You've heard of square roots, but they're also cube roots, fourth roots, fifth roots, things like that. So if you do 5 squared is 25, remember powers and roots, the square root of 25 is 5. Powers and roots are inverses of each other. Speaking of inverses from section 1.3, they're inverses of each other in that way. You can go backwards as you can go forward. And that's kind of the big talk on having rational exponents with radicals and such, and you can work that out. You can also write an nth root of A as a power of A. If you assume the power of a power property applies to rational exponents, then the following is true. If you take a to the 1/2 squared, you get a out because you multiply the 1/2 with the 2, and half of 2 is 1, a third of 3 is 1, a quarter of 4 is 1. This is kind of like a therefore. Therefore, if you're going to square something to get a out, and we can square the square root of something, excuse me, I wrote that wrong. You can square the square root, I can't write this. You can square the square root of something to get that thing back out. Then it makes sense that a to the 1/2 is equivalent to the square root of a, and that's what they're saying. The square root of a equals a to the 1/2 power. Similarly, the cube root of a is a to the 1/3 power, and the fourth root of a is a to the 1/4 power. In general, the nth root of a is a to the 1 over n power for any integer n greater than 1. So the denominator in an exponent is equivalent to the root of your value that you're doing. So the nth root is also to the 1 over n. Now this 1 could be any other number, like 2, whatever, but then this would be a squared. The nth root of a squared, things like that. So I don't know if they'll hit any of those here. Real nth roots of a, let n be an integer greater than 1 and a be a real number, if we're talking about doing nth root of a right here. If n is odd, so if we have an odd root, then a only has one real root. That's because a can be positive, negative, or 0, and you can take its root appropriately, so that's all good. The nth root of negative a is negative a over whatever, as long as n is odd. You can't take the square root of a negative number, but you can take the cube root of a negative number, or the fifth root of a negative number, and that works out. If n is even and a is greater than 0, so this time a needs to be positive because we take square root, fourth root, whatever, to have a real root. You can have 2 real roots, whether you're taking the positive square root of a number, you get a positive result. Negative square root or fourth root, even root of a number, you get a negative result. So you can't take the square root. You can't take the square root of negative 25, but you can take the cube root of negative 8, right? You get negative 2, something like that. There can be a negative outside of it, though. If n is even and a equals 0, then the square root of 0 is 0, and that applies. If n is even and a is less than 0, then there are no real nth roots, just like I was mentioning there. Okay. So those are 3 cases for evens, specifically when we talk about square roots, but because this is a radical section, they'll probably talk about more. Okay, so some examples that they refer to here, n representing the root and a representing this guy here, find the real indicated roots. So the cube root of negative 27 in this case would be negative 3. And then here we can take the 4th root of 16. And they want to refer to, it appears, and I have to look at this as well and make sure that I follow up on the example the same way. There are 2 different ways that you can get 16, from 2 to the 4th and negative 2 to the 4th. Therefore, there are real roots of positive and negative 2 from not taking the 4th root of 16, but taking the positive 4th root of 16 and negative 4th root of 16. So you consider both with it. Make no mistake, the 4th root of 16 is positive 2. But the negative 4th root of 16 is also negative 2. So there's kind of an interesting thing in there that I also have to consider with the negatives. I have to make sure to know when to talk about it and when not to. So here we can take the cube root, etc. Well, I'll move forward. After that, okay, so here are more examples where they spell them out. Evaluate each expression. So these ones are straight up evaluate them as they are, sign and all. I don't know if they're going to give us ones that aren't possible. The cube root of negative 8 should be negative 2 because there are 3 negative 2's to multiply to become negative 8. The negative cube root of 8 is also negative 2 in that sense because the cube root of 8 is 2 and then apply the negative. 16 to the 1/4 is the same as the 4th root of 16. So they show that right here. It's the 4th root of 16, boom. And the 4th root of 16 is 2. Just 2, not negative 2. But then you get, this won't work. You get the 4th root of negative 16. You can't take the 4th root, where is that? They don't write it. But the 4th root of negative 16, you can't take an even root of a negative value, so there's no real solution to that one. Let's see what they said. It's not a real number because there's no real number that can multiply. It's also known as an imaginary number or complex number in that case. Okay, I mentioned that. Okay, so they're kind of showing this right here. If you raise to the m over n power, not just 1 over n, but the m over n, then it's also to the mth power on top of that. So 27 to the 2/3 is the cube root of 27 squared, whereas 27 to the 1/3, which is the cube root of 27 to the 1st power. So cool, we will be evaluating those. So 16 to the 3/4, now they do a split this way. They raise to the 1/4 power. I tend to write the 4th root of 16 cubed, like that. And by the way, let me mention this. You can take the 4th root of 16 cubed or the 4th root of 16 cubed. What's the difference? Either cubing 16 first or taking the 4th root first. You should arrive at the same result. I'm trying to think if there are exceptions, and I'm not coming up with any. I'm thinking about if there are negatives inside and you take an even root, but I think you can always reduce a fraction. But anyway, but I recommend this. And the reason is because you get to smaller numbers first. I don't know what 16 cubed is, and I don't know what the 4th root of that, well, I know what the 4th root of the big number is now, but if I take the 4th root of 16 first, I get that small 2, and then I cube the 2 and I get the 8. So these are the same thing, but I recommend that you do the root first and then the exponent second. It seems like the book's doing the same thing as far as showing that. 27 to the 4/3, same thing. Take the cube root of 27 first to get 3, raise it to the 4th power to get 81. And then some real life problems. That is a big ball. We are looking at an example of a radius of a sphere given by this equation. You know what's interesting about this? I'm looking at it. So this V is volume, R is radius, and I think we had a previous video that did volume as 4/3 pi r cubed. So apparently if you do a rewrite of this formula, it looks like you get this right here. So it's a reimagining, solving for r, multiply by 3/4, divide by pi, take the cube root, and boom, you get that. Or they wrote to the 1/3 power, which is the same as the cube root. V is the volume, find the radius, use 3.14 for pi, which I generally wouldn't do. So volume's 113, substitute that into here, pi is 3.14, evaluate, find your radius, about 3. Okay. And then another problem here, calculate the annual inflation rate of an item that increases from P to F over a period of n years. You can use this equation. Where's R? Inflation rate R. Okay, so this, well, I generally don't use F. I generally use A, I guess. But this equation is a rewrite of A equals P times 1 plus R to the n power. So they use this version of this equation. They divided by p, took the nth root, raised to n1 nth power, and subtracted 1 from both sides. So they're using common equations that you would have here, getting r by itself, making a different version of it, which is fine. I don't care. That's perfect. It's the way we just talked about inverses. You make the input the output, or vice versa. And then you can solve for the rate by substituting other values. So the principal, and I guess F stands for the final. The final values, substitute those into there over the course of 5 years. That is n. Plug those in, and you get a rate of 0.03 as a percentage. That's about 3.3%. Okay, so it looks like we get to move forward to some of this stuff here. Let me go over the vocab and concept check, and then we'll do the problems that are involved. I cannot remember for the life of me how many problems there are. There could be 30, there could be 70. I actually don't know. Explain how to evaluate 81 to the 1/4 power. So let's make sure that we know not only how to do it, but what to avoid doing as well. This is not 81 and a quarter, as in 81 plus 1/4. It's also not a quarter of 81, or 81 times 1/4. It's neither of those. This is 81 to the 1/4 power, which is the 4th root of 81 to the 1st power. And you have to figure out what number multiplies to itself 4 times to get 81, or use your calculator for that, or whatever. But anyway, that's 3. That's 3. After you do them several times, you should get pretty familiar with what are some of those powers or roots over time. Like, that's why sometimes it's like, hey, what's 6 to the 4th power? And like, how I know it's because I've seen it a lot. Which one doesn't belong? Which expression doesn't belong with the other 3? If you've seen this from me before, if I call this one A, I'll find which other ones are like A and which one's different that's like B. The cube root of 27 squared. So the cube root of 27 is 3, and 3 squared is 9. Now, I don't see a 9 here, but I do see 3 squared, so I'll call that A. This is 27 to the 2/3, which is equivalent to the cube root of 27 there. That's also A. So this must be different. Yeah, this is the square root of 27 cubed. Clearly different from the first one, and apparently different from the other two. So this one's different. My reasoning is, well, clearly this is different from that because the numbers are switching places. These ones are the same because the cube root of 27 is 3, and this is the rational exponential form where 3 in the denominator of the exponent also represents the root, and the numerator is the power. Okay, so with those in mind, we are going to go ahead and move on to the core problem set here. We are going to start with number 3 and move forward from that. Excuse me, let me go back to this and figure out where I want to switch to. Let's try that again. Boom, that looks much better. And we are doing numbers 3 through 56. 3 through 56. Okay, hold on, let me get everything set up now. So it was somewhere in between what I said, between 30 and 70. Let's have some fun. Okay, number 3 and 4, we are going to rewrite the expression in rational exponential form. So these are straightforward. There's really no work. Well, there's some work to show. The square root of 10, if you recall, that is the second root of 10 to the 1st power. Therefore, that is equivalent to 10 to the 1/2 power. It's probably better that you just know square roots mean to the 1/2 power, and that'll help resolve a lot of things. But that's a justification for that reasoning with those numbers, because those were implied. Those were never there in the first place. All right, number 4, we have the 5th root of 34, which is going to be 34 to the 1/5 power. Now, by the way, they're not asking us to evaluate these. These are not perfect whole number values. They are some irrational repeating forever decimal. They're just asking you to rewrite them in that form, so you're aware of what to do with them. And to be honest, there's not much use to me going from this form to this form unless I'm using variables. And I don't know if this stuff's going to touch variables. The examples didn't touch variables, so I assume we probably won't. But if we start talking about variables, or if we have to wait till IM3 for that, you'll see why sometimes that's preferred for variables. I generally prefer to use the radicals instead, though. All right, number 5, let's write the number. It's 15 to the 1/3 power. We are going to rewrite in radical form. This is the cube root of 15 to the 1st power. But of course, I'm not going to evaluate that. And number 6, 140 to the 1/8 power is also the 8th root of 140. Okay. 7 through 10, let's find the indicated real nth roots of A. So this is where I have to be conscious of that if I have an even root, and then I'm talking about the a being greater than 1, that I have to consider the positive and negative forms of that, and I will be doing that. So number 7 is an example of that to my knowledge. N equals 2, that is the root. A equals 36. They're asking us to take the second root of 36. But consider its plus or minus form, because the values that you can square to get 36 are positive 6 and negative 6. So those are the two roots of that one. Number 8 looks to be under the same premise. It is an even root, and a is a positive value. So we are going to be taking the fourth root of 81, understanding that 81 being a positive number, when you raise a number to the fourth power to get it, it could have been the positive or negative version of the value. So we are looking at plus or minus 3. 3 to the fourth is 81, negative 3 to the fourth is 81. Oops, I didn't switch this number 8 here. Apologies. Number 9, we are going to take the cube root of 1,000. So let's take the cube root of 1,000, and that is just 10. It's not negative 10, because negative 10 cubed is negative 1,000. As we have an odd root, that's what's going to happen. And number 10, n equals 9, a equals negative 512. If n was an even value, which it's not, then there wouldn't be any real solutions. Because it's odd, we can take the ninth root of it. And that number happens to be, if I'm correct, negative 2. And it will be negative, not the positive. Oops, I didn't switch to number 10 there either. Sometimes when the problems are really quick, you'll see me do that every so often. Sorry. All right, numbers 11 and 12. Let's find the dimensions of the cube. Let's check our answer. Okay, it's at, oh, I didn't see the volume above it. Sorry. So the volume is 64. So the volume of a cube is taking all three cubes, all three sides of the cube, edges, I should say, and cubing them. Because they're all the same, length times width times height. So your volume is 64, and that equals s cubed. In order to solve for s, see, I don't know if this is where the book would go more in favor of, you have to raise it to the 1/3 power, because then it multiplies by 3, and 1/3 times 3 is 1, and that's why it goes away. But my version of this saying that is, you take the cube root of both sides. And 64 to the 1/3 is also the cube root of 64, which is 4, and this is in inches. So 4 inches for number 11. Number 12 is the same, pretty much everything, only a different value. And this time I won't say raise to the 1/3, but 216 equals this, s cubed. And this time let's take the cube root of both sides. With that in mind, the cube root of s cubed is just s, and then you are left with s equals 6 centimeters. Okay. Numbers 13 to 18, let's evaluate these expressions. These ones are where, and I guess here on out, unless we're solving something algebraically, see, we're not finding roots anymore. We are evaluating the thing that's here. Number 13, the fourth root of 256, means we're only referring to the positive version of it. There's no negative in front of what we're talking about here. So what number to the fourth, what number times itself 4 times is 256? That's 4. So that is number 13. Number 14, the cube root of negative 216. Odd roots are okay for negatives. That should be negative 6. I think that question was actually technically already asked. Was it not? Or wait, did we just do 6 from the cube question? I can't remember anymore. 15, same thing. The cube root of a negative. Negative 343. This is negative 7. 7 cubed is 343. I don't know that must be 4, I guess, huh? Number 16, the opposite of the fifth root of 1024, which is the opposite of, so 4 times 4 times 4 times 4 is 256, times 4 should be 1024. So negative 4. Number 17, This is a rational exponent, 128 to the 1/7th power. Let's rewrite that as the 7th root of 128, or let's perceive it that way at least. And that's what happens when you multiply 2 7 times. So you get 2. And then number 18, we have negative 64 to the 1/2 power. Now, negative 64 is in parentheses. That means we are taking the square root of negative 64, which is not possible. We cannot evaluate that. If you start to get into imaginary numbers, it'll be 8i. So if you're on that front, great. But Big Ideas Math is not ready for you yet on that front. In exercises 19 and 20, rewrite the expression in rational exponent form. So the same thing as the previous ones, only now we actually have a power involved with it. So number 19, we have the 5th root of 8 to the 4th power, which becomes 8 to the 4/5 power. They're just asking for the rewrite, no evaluating, and that's it. So these are kind of the best practice problem. Not the best, but they are nice must-dos to make sure that you are just aware of what's going on with it. So the 5th root of negative 21 to the 6th power is negative 21 in parentheses to the 6/5 power. The power is the numerator, the root is the denominator. Okay, let's move forward. Numbers 21 and 22 we will rewrite in radical form, these expressions in radical form. So let's go, and this is the direction that I would generally go to evaluate these if I needed to, or if I could by hand. In this case, I can't really. Negative 4 to the 2/7 power, because it's in parentheses, make sure that that's all inside that radical hat. 7 being the denominator is the root, and the 2 exists, say, there. Yeah, that's fine. I was going to say you can put the 2 inside, just make sure you put parentheses around it like that, but I think they kind of want you to do this. I wouldn't mind you doing this as well. That's probably the best look for this kind of question when it comes to perception. You'd want to take the 7th root first before you square it, if you actually knew how to make that so. Number 22, and this is one I could evaluate. They're not asking me to, but you could. 9, like I could in my head. 9 to the 5/2 is the square root of 9 to the 5th power. And as far as just mentioning, evaluating that, notice that I'd rather do the square root of 9 first to get 3, and then raise that to the 5th power to get 243, rather than take a guess at what 9 to the 5th is. I don't know what it is. And then take its square root. I'm not sure. Notice that I didn't write the 2. The square root has that implied there's a 2 there. Remember, it's not a first root. If it's implied, it's a square root. Okay, now we evaluate these ones. So I guess 22 is good practice for that. But now let's actually make it happen. So number 23, we have 32 to the 3/5 power, which evaluates to the 5th root of 32 cubed. The 5th root of 32 is 2. We will cube 2 and get 8. So that's how that goes. Again, I don't know 32 cubed, and they're not asking you to use the calculator. They're expecting you know some of these perfect value things. And we're not simplifying radicals either, as like if you know that like the square root of 8 is 2 root 2, things like that. We're not doing that kind of stuff here. So I imagine that these are all going to have perfect results, as in this is a perfect cube. If it wasn't, then they wouldn't give it to us. The cube root of 125 is 5, and 5 squared is 25. And the reason I bring that up is because even if you don't know what the answer is, and you're like, I gotta use the calculator, you kind of gotta try. If I told you that it's for sure a perfect cube, then try numbers. What, 2 times 2 times 2, 3 times 3 times 3, things like that. You'll notice how fast, how quickly those numbers get large, like really fast, right? 8 cubed is already, I think, 512, or I think that's right. And so they jump up really fast, and this number ends in a 5. So not only does it have to be an odd number, it has to be a 5. No other odd digit multiplies to itself to get a 5. So it's like that kind of thing that can really assist you as well. Number 25. Negative 36 to the 3/2 power is the square root of negative 36 cubed. If we're talking about real numbers, this is not possible. Cannot take the square root of a negative number let alone any other real root of a real number. So nothing is nothing to evaluate. So your calculator will say domain error, or what mine would say domain error. Number 26, on the other hand, appears possible. Negative 243 to the 2/5 power. So this will be the 5th root of negative 243 squared. This is one of those things, once again, like what number could it possibly be? You might try something like 5, but you realize you get too big and it needs to end in a 5. 7 would be too big. It's kind of got to be 3, and it is 3, or in this case, negative 3. And negative 3 quantity squared is 9. All right, 2 more, 27. Negative 128 to the 5/7 power. That'll be the 7th root of negative 128 to the 5th. Now, I think we already did one of these with 128, the 7th root, and that is 2, or in this case, negative 2. And negative 2 to the 5th is negative 32. That stays negative because it's an odd power. And finally, number 28, you have 343 to the 4/3 power. That's the cube root of 343 to the 4th, which is 7 to the 4th. And I don't know 7 to the 4th. 21 to 301, 2401. I'm gonna say 2,401. Sorry if it's wrong. You can do that part in your head if you'd like to. What else was I gonna say? Oh, maybe not. Here on out in some of these, I might not write this step if there are a lot more things to do stepwise. So here I might say, in the cube root of 343.7, and then to the 4th power. So like, or I might go straight to this step instead of writing the root thing out, because it seems like the book doesn't even do this a lot too. Maybe they're trying to, get you to go that way on it. Maybe, I don't know. Okay, let's go to number 29 and 30 on error analysis. Was there no instructions? Describe and correct the error in rewriting the expression in rational exponential form. So let's just look at it. They have the cube root of 2 to the 4th, rewritten as 2 to the 3/4 power. Their mistake is the 3 is the numerator in the exponent and the 4 is the denominator, when it should be the other way around, because that cube root of 2 is also 2 to the 1/3 power. So the numerator and denominator of the rational exponent are switched. I mean, I described kind of the rest of it, and let's write that proper answer. So instead, let's correct and say the cube root of 2 to the 4th is 2 to the 4/3 power. If you want an in-between on that, that is the 2 to the 1/3 to the 4th. And then you multiply the 1/3 with 4 to get 4/3. Okay, number 30, describe and correct the error in evaluating the expression. So negative 81 to the 3/4, well, I already know where this is going. Negative 81 to the 3/4 power is, so notice how they did this. Negative 81 to the 1/4 cubed, so they went ahead and separated that, which is fine. But this is where they went to evaluate, and you would often see me rewrite this as the 4th root of negative 81 and go from there. So either or. Now the 4th root of 81 is 3, that's correct, and the opposite of the 4th root of 81 is negative 3. But this is the 4th root of negative 81. And 4 being an even root means that's not possible, whereas they actually wrote a value there. So this is the hiccup, if you will. You cannot take an even root of a negative number. You cannot take the even root of a negative number. This is not possible. And that's my answer. This is not possible. So when they're saying, solve the problem, I am, you get to that step and you say no. Okay, numbers 31 to 34. Let's evaluate the expressions. This time they're dealing with possibly some values that are greater than 1 in the numerator of the rational exponent. But not on 31. Number 31 is 1 over 1,000 to the 1/3 power. Now this does, whether you treat this as two separate numbers or a fraction, whatever, this does apply to that power of a quotient Yeah, power of a quotient property from before, where we would do 1 to the 1/3 over 1,000 to the 1/3, like so. So you apply it to both, which is the cube root of 1 over the cube root of 1,000, which is 1 over 10. So whichever way you want to put it, it's up to you when you're doing that, but that's the main process on how all that goes. So I probably won't do all of that next time. And this is that next time. 1 over 64 to the 1/6. The sixth root of 1 is 1. The sixth root of 64 is 2. So 1/2. Oh, I didn't flip that over. And inversely, 1/2 to the 6th power is 1 over 64. Number 33, we have 27. Okay, we have 27 to the negative 2/3 power. So there are a couple things involved here. This might be a time where, because I'm going to convert to its radical form, that's fine, but I never, in my history thinking about it, I never deal with negative radicals, like the negative second root of something like that. I always use it in this form. So it's best that I begin by rewriting it like that, 1 over 27 to 2/3. And then if I like to go ahead and convert to this form, it's the cube root of 27 squared, but 1 over that. The cube root of 27 is 3, and 3 squared is 9, so I get 1/9. I don't think these were in the examples like this. Maybe they were in the ones that I skipped. Lastly, number 34, 9 to the negative 5/2 power. Same thing. Not the same answer. Well, maybe it is. But 1 over 9 to the 5/2 power. Let's see if we can kind of do this part in our head. We are going to be taking the square root of 9, which is 3, and 3 to the 5th is 243. Okay. Let's move forward. Number 35 and 36 are problem solving, two completely different problems. A math club is having a bake sale. Find the area of the bake sale sign. So they have, the area is going to be the length times width. So this area, we are going to multiply the sixth root of 729 with, 4, I was going to say 4.5 feet, with 4 to the 1/2 feet. So pretty much they want you to evaluate these guys here. I know the cube root of 729 is 9, so the sixth root must be 3. So that's 3. And 4 to the 1/2 is the square root of 4, which is 2. Now be careful, because 4 times 1/2 is also 2. So don't start mistaking it for saying that, like, yeah, these are all 2. Anyway, so this is 6. That's 6 square feet. That is the area of the bake sale sign. Okay. It's a 3 by 2. 3 feet by 2 feet. Why didn't they just say that? Oh, wait. I want to see it. Pie is sweet. Math club. Bake sale this Saturday. Okay. Number 36. The volume of a cube-shaped box is 27 to the 5th cubic millimeters. Find the length of one side of the box. So these unknowns, when you cube them, you get the volume. So x cubed is 27 to the 5th. Right? Is that right? I think so. Volume, yeah. So we are going to take the cube root of both sides, like that. And now we're going to have x equals the cube root of 27 to the 5th. Remember, you can do the cube root first and then to the 5th power after, and I will. Cube root of 27 is 3. 3 to the 5th is 243. And this is in millimeters. Millimeters. That's the length of each side of the box, or an edge. Number 37. The radius r of one of the base of a cone is given by the equation. And I mentioned, no, well, I didn't for this one. I think we were talking about a sphere in the lecture portion, if you heard that. But the volume of a cone is 1/3 pi r squared times height. So I'll just show this to you right here. If you wanted to solve for r, get r by itself, you could multiply both sides by 3. So this guy goes away here. And you could divide both sides then by pi times h, like that. So these guys go away. And then you could take the square root of r. So you get that. So r is the square root of this, or that to the 1/2 power. So you can see where their equation comes from. Now, when it comes to me evaluating it, I think they're going to ask us to find the radius and evaluate it. I'll just do the square root. Okay, v is the volume, h is the height, all that stuff. So volume is 5 inches, cubic inches. The height is 4 inches, and we're just substituting. So I was just showing you how it's a rewrite of that formula, just like the other ones were. So 3 times 5 over 4 times pi. And they are asking us to use 3.14. I don't know why. I'll just say pi in general. I'll just hit the pi button. It should round the same way. I get it because maybe they're... Well, actually, no, I don't get it. Maybe they just don't assume you have a pi button on your calculator, but you probably should. So 15 over 4 pi. We're going to take the square root of 15 over 4 pi, basically. So I have a calculator. Let me bring it up. So I'm going to do the square root of 15 over... Now be careful with this. I'm going to say 4 pi, but I got to put it in parentheses on my calculator, because otherwise it'll assume pi is in the numerator of my problem. So I'm getting this number. Round to the nearest inch, so around 1.1 inches. I doubt if I use 3.14, then suddenly it's going to be 1.2 inches or 1.0 inches. Now, if you wanted to raise it to the 1/2 power, you could. So I could say over 4 pi to the 1/2. Only here I also have to use parentheses around that for the sake of what we have, and we should get the same answer. So raising to the 1/2 power and taking the square root are one the same. So 1.1, they said to the nearest... to the nearest inch. So 1. So 1 inch. All right. Number 38. It's another modeling with mathematics. The volume of a sphere is given by the equation here. Where S is the surface area. I was going to say, okay, maybe. And I could spend some time trying to get that to work with you as well, because the volume, as I stated, is 4/3 pi r cubed. I'm sure this isn't why you're here for this. The surface area is 4 pi r squared. And if you got r by itself, let's see, how would you say that? If you got r by itself, then yeah, if you got r by itself here, then you could rewrite this. I'll put S for surface area. S over 4 pi and take the square root, and then you'll get R equals the square root of that S over 4 pi. Anyway, if you substitute that into here, then you could end up getting that they have here. So it's some form of a rewrite. If I wanted to spend time on it, I could. I feel like you guys are here more for the problem, though, when they give you the formula. Now, S is the surface area. Find the volume of a sphere to the nearest cubic meter that has a surface area of 60 square meters. Okay. So, and there are other ways, by the way, sort of other ways I would do this. If I had the surface area, I would use it to get the radius, and then I would plug that radius into here. So, yes, that literally is what that formula is for. Instead of teaching you what the volume and surface area formulas are for this, you can just practice your radical thing straight up, I guess. So what are we doing here? Volume is 1 over 6 root pi times the surface area to the 3/2 power. So 1 over 6 root pi times 60 to the 3/2 power. And I'm going straight to the calculator. I don't know the square root of 60, and the rest of it I'm going to have to do as well. So going back to there, let's find that. Let's do, I don't even know what I wrote. 1. Well, not even 1. Let's write the 60 up there. 60 to the 3/2 power, or 1.5. There are a lot of ways you can type this portion in the calculator. Over 6 root pi. And have that in parentheses as well, because it needs to be in the denominator. So 43.7. What do they want? Nearest cubic meter. So around 44 cubic meters. Was the other stuff in meters as well? Yeah, square meters. Okay. Now, it is possible if you use 3.14 here that maybe it turns into 43 instead of 44. I don't know. Unfortunately, I'm ignoring the books. You'll see me ignore a book's process sometimes, and that's going to be me here. I like to attend to precision. Explain how to write that in rational exponential form. Well, I know what the conversion is. I believe their explanation will be a different story. So for number 39, the nth root of a to the m power. The explanation I'm sure that they want is you rewrite the nth root of a as a to the 1 over n power. And then using the power of a power property, you multiply 1 over n with m, and that then becomes a to the m over n power. But if you are savvy enough to go from here to here immediately, you do it. For the sake of the problem and explaining, I get it. Number 40, how do you see it? Write an expression in rational exponent form that represents the side length of a square. Write an expression in oh, I see. Okay, so your square area is x. It's not x squared. That says x square inches. It's x. The side length of each of these will be taking the square root of this, right? Because if I were to kind of demonstrate an algebraic form here, let's say this was y. If one side length is y, so is the other one. And the area is y squared, y times y. So if y squared equals x, and you have to solve for y, then you take the square root of both sides. Y is the square root of x. But they want rational exponential form, so that's going to be x to the 1/2 power. I wrote more than what was needed, but I want to make sure you understood why I was taking the square root in that. And remember, the other thing's not squared. Oh, I also need the units. This is going to be in inches. Okay. Number 41 and 42. Now, I showed in the lecture portion how this formula comes to be from something else, but we are going to go ahead and use what's here. To find the annual, use this formula to find the annual inflation rate to the nearest tenth of a percent. And by the way, we have to convert this from decimal to percent form in the very end. A farm increases in value from 800,000 to 1.1 million over a period of 6 years. So the F is the final amount. That will be 1100000. P is the principal amount. That is 800,000. And again, it's one of those, if you're really savvy things, you could have gotten rid of all these zeros right here, but I'm good. And n is 6. N is the number of years, or the number of instances that you're counting, in this case years. So if those are your three items, this is going to be R equals 1100. Those two numbers raised to the 1 over 6 power minus 1. And that's where you basically let your calculator do some evaluating for you. So let's go ahead and take a look at that. That'll be that over that raised to the 1/6 power and then minus 1. So the value we're getting is 0.0545. Okay. There are other numbers there, but they want us to round to the nearest tenth, one decimal place, so I want to make sure I have that. Now, I'm not rounding this number to the nearest decimal place. It's the percentage I need to round to there. So this is around 5.45%. When you multiply by 100, you shift the decimal 2 places over, or around 5.5% to the nearest tenth. Okay. Same thing on this one. The cost of a gallon of gas increases from $1.46 to $3.53 over a period of 10 years. So let's identify again. The final is $3.53. The principal is $1.46. Principal means initial. To the 1/10 power minus 1. Back to the calculator we go, and we're going to get All right, 0.0923. So that should be 9.2%. 0.0923 is around 9.2%. So what you were doing in these situations, just so you know, is that this, what was it, milk? Oh, gas. This gas was increasing around 9% every year for 10 years. A gallon of gas. So it went from 146 to 353 over that time, increasing about 9% every year for 10 years. That's the idea, that what you're doing in that. Number 43, in reasoning, for what values of x is x equal to x to the 1/5 power? When does x equal x to the 1/5 power? I don't know if they're asking for guess and check. Let me tell you some off the top of my head that I know. 0, 1, and -1. I'm trying to imagine other ones there. 0 equals 0 to the 1/5. 0 to the 1/5 is 0. 1 to the 1/5 is 1. And -1 to the 1/5 is also still -1. It stays negative in that case. Let me think if there's an algebraic form for that. What I could do is I could raise both, and I don't know if this is beyond us because this deals with some algebra stuff that we kind of can't play with quite yet. Yeah, so, okay, this part right here is going to go beyond, what is it, reasoning? This is going to go beyond the scope of what you probably know at this stage of math. So you can feel free to move on to number 44 if you're not sure what I'm about to do. I'm raising both parts to the 5th power, and this will become x, and this part's x to the 5th. X to the 5th equals x, and I can subtract x from both sides. I can factor an x out of here to be left with x to the 4th minus 1. This leaves you with a difference of 2 squares in x squared minus 1 times x squared plus 1. This leaves this part with a difference of 2 squares in x minus 1 and x plus 1. And using zero product property, x can either equal 0. If x minus 1 equals 0, then x equals 1. If x plus 1 equals 0, then x equals -1. And these are not real solutions. No real solution. So therefore it is those three. That's something algebraic that you probably don't know at this point. I am reasoning myself algebraically in a way that I know how to do. So yeah, just making sure those are the three answers, 0, 1, and -1. Sorry, let's go back to that one quickly. How did I reason that before this algebra stuff? Because the numbers have to be the same. And if you start taking the 5th root of any number that's more than 1, then the numbers start to become smaller than the original number. And if you start to take the 5th root of a number that's between 0 and 1, then the numbers start to become larger than your original number. 0 doesn't change, 1 doesn't change, and -1 not only doesn't change, but it can stay negative while you're doing it. That wouldn't apply to x to the 1/4 power for a -1. All right, number 44. Making an argument. Your friend says that for a real number a and a positive integer n, the value of the nth root of a is always positive, and the value of the opposite of the nth root of a is always negative. Is your friend correct? Explain. Not always correct because it says any real number a. It says a real number, so hold on. Your friend is incorrect because it says for any real number a. And if a is 0, let's start with the easy one. If a is 0, then those values aren't positive. Now, it only takes me to dispute one thing for me to be correct in saying the friend's incorrect. But if a is negative, and notice how they say a positive integer n, that means n can be even numbers. If a is negative and n is even, there aren't any real values. Now, if a was positive and n was odd, excuse me, if a was positive, yeah, if a was positive, you're good. If a is positive, then you're good. Then that would be correct. Otherwise, that's the answer for 44. All right, number 45 to 48. Simplify the expression. Oh, they do have some algebra ones here. Okay. They just didn't I don't think they did them in any of the examples. We didn't see them, at least. Okay, this might be where I start talking about some of the stuff here. Y to the 1/6 to the third is the same as multiplying the 1/6 and 3, so it becomes y to the 3/6, which becomes y to the 1/2, which becomes the square root of y. Now, this could be some version of an answer, but when you have the same roots for both of them, you want to put them together, and I want to put them together alphabetically. It becomes the square root of xy. Now, they didn't state whether or not they want it in radical form or rational exponent form. For the most part, to my knowledge, radical form is the preferred version of this. That's what I like to see, especially when numbers are involved. This didn't have any, but especially when they are. You don't want to be inconsistent and have two different things. Next one is y times y to the 1/3 raised to the 3/2 power. I like to simplify the inside first. Y is y to the first power, and 1 is the same as 3/3. And I mention that because when I multiply these at the same base, I can add the exponents this way with a common denominator. So that'll get me y to the 4/3. If you raise that to the 3/2 power, we get to multiply 4/3 with 3/2. 3 over 3 is 1, and 4 over 2 is 2. So you're left with y squared. Y squared. Number 47. And these ones go in the form... I don't know which things they expect you to already know and which ones they don't expect you to know. Like, as far as what things you're allowed to do. X times... Okay, so here's one of these examples. Notice where this says the cube root of y to the 6th. And then this other one here says the cube root of x cubed. Keep in mind how exponents aren't the same as numbers, right? The cube root of 6, I don't know what that number is. But I know what the cube root of y to the 6th is, because we're not taking the cube root of 6. You know what we're doing? We are... Sorry, I tried to change the color. We are dividing 6 by 3. Now, this is the reason why rewriting it in rational exponential form may be helpful for you with variables, whereas with numbers, I make more sense of the cube root aspect of this. But here, the 6 divides by 3. I personally will probably avoid doing this more often than not, meaning saying I'm just going to straight up say 6 divided by 3. In this case, I'm going to say 3 divided by 3, and I hope that's okay. There are only 2 problems I have to deal with, but you'll probably just be ready for that. Anyway, that's what we're doing. Y to the 6/3, y squared. And this has a y squared as well, and this is x to the 3/3. You do 3 divided by 3, which is 1, and that gets you x. Now this gives you xy squared plus xy squared when you write them like in order, and you can combine like terms. 1xy squared plus 1xy squared is 2xy squared. Lastly, number 48. What time are we at? Not even an hour. Good. And that's with a 15-minute lecture. Lastly, number 48, we have x to the 1/3 times y to the 1/2 to the 9th times the square root of y. Now again, it's one of those things. Would you rather work with this as it is? I guess so, yeah, when it's power of a power. These can't combine. We won't try and add these different bases. So this time we have to apply the 9 to both of these here. So x to the 1/3 to the 9th is x to the 9/3, which is x cubed. Y to the 1/2 to the 9th is y to the 9/2. That can't reduce. And this has the square root of y. So would you rather, let's do this. Let's turn the square root of y into y to the 1/2 power. Okay, I can see the purchase for rational exponential form as you're computing here. I think it seems to make sense. Now, you get to add these two here, common denominator, and 9 plus 1 is 10, so it's y to the 10/2. Don't convert this into rational form, divide 10 by 2, and you get 5. So x cubed, y to the 5th. Okay. All right. 49, let's see how many we have left. Up to 56, so 8 problems left. 49, problem solving. We have I don't know how many faces that is. Oh, they say dodecahedron, so 12-faced shape. The formula for the volume of a regular dodecahedron is this. I didn't know that. Where L is the length of an edge. The volume of the dodecahedron is 20 cubic feet. Estimate the edge length. So on number 49, the volume is about 7.66 cubic edges cubed, and the volume is 20 cubic feet. So 20 is about that. I'm just going to keep using the approximated symbol because they gave it to us, and this will definitely be approximate. Let's divide both sides by 7.66. Now, one thing I want to mention here, unless dividing this gave you an exact answer, don't round this part early, meaning I'm going to leave this as 20 over, approximately, 20 over 7.66. And I'm going to use that part in the calculator when the time comes for it. But first, let's do it as cube root. So I'm going to type this in the calculator. I'm not taking 20 over 7.66 first, rounding that early, and then taking the cube root. So if you ever hear me say that in a lot of other videos, yeah, don't round early. That was kind of the same thing with pi. I don't want it turned into 3.14 beforehand. Now, I have a cube root button, but if you don't know, okay, here, let's do this. If you don't know where the cube root button is and you can't work with it and it's test day, then do this. This is probably what they want you to do anyway. 20 over 7.66 to the 1/3 power. So you know where the square root button is probably. You might not know where that cube root button is. Now, on this particular calculator, it's actually in the math portion right here. Like that, the cube root of. But maybe you don't know that. So let's do this. In parentheses, 20 over 7.66. And that's all raised to the, in parentheses, 1/3 power. Now they said, estimate the edge length. So they didn't say what's around to. I'm going to go to what's significant. Notice the 999 that comes up. So I'm going to call it 1.377. Around 1.377 feet. So for you guys, like that. Yeah, they didn't tell us what to round to. I imagine 2 decimal places is pretty good because they had 2 decimal places here. But that's what I'm going to stick with. Okay, number 50. Thought-provoking. To find the arithmetic mean of n numbers, divide the sum of the numbers by n. To find the geometric mean of n numbers, a sub 1, a sub 2, a sub 3 to a sub n, take the nth root of the product of the numbers, like they show you. Compare the arithmetic mean to the geometric mean of n numbers. Okay. So in other words, with arithmetic mean, you add these. I mean, I know what an arithmetic mean is. I don't know what they want me to do. So this is what an arithmetic mean. So arithmetic mean means find the average. Add them up, divide by how many there are. Geometric mean is exactly what you're seeing there. Nth root of multiplying those things. I don't know what they mean by compare, like divide this by this and say it's this many times larger or smaller. It was, I don't know if it was last section or the one before. There was another one that I think said thought-provoking in one of these boxes and stuff. And I think I made a mistake on how to do the problem. I was thinking more algebraically than not, whereas I think the book really just wanted you to come up with an example, like as an open-ended. I don't know if that counts as open-ended, but it says like come up with your own. Come up with your own. And maybe that's what this is as well. If that other one's thought-provoking, then it's open-ended, come up with your own. So let's do that. Let's come up with our own. And then let's compare them, shall we? Because honestly, I don't know the answer. I don't know if geometric means are larger or smaller than arithmetic means. I have no idea. It seems like you'd think geometric means would because the multiplication, but then you take a root of it. Or maybe they're the same, in which case that'd be cool to do. So let's try it. Let's pick like 6 numbers. Let's do 3, 10, 13, 16, 25, and 60. All right, so I have 6 numbers here. Let's find its arithmetic mean. I'll call it AM. So we're going to do 3 plus 10 plus 13 plus 16 plus 25 plus 60 all over 6. I don't know if this is how you're supposed to do the problem or not, but I'm just making it up. So I'll say example in case you're not listening and you're just watching. I should probably use the calculator, but let's see. 13 plus 13. Oh, I didn't notice that. 26, 42. I'm going to mess up. 67, 127. So 127 over 6, which is 21 and a sixth. So I'm going to guess the calculator is going to say 21.16 repeating. Let's see if I got that correct, because I could have messed up a lot of different ways on that. 3 plus 10 plus, no, 3 plus 10 plus 13 plus 16 plus 25 plus 60 divided by 6. All right, 21.16 repeating. Okay, the next one we're going to do is geometric mean, which is multiplying these. Normally you do the geometric mean just between two numbers. Not that you have to, but that's normally when it's established what you do, at least in geometry. Oh, my camera's got a mind of its own. And it is, what are our numbers? 3 times 10 times 13 times, yeah, I'm actually genuinely curious as to what this is going to be. So I'm not doing that in my head. So let's see. The sixth root, to the 1/6 power, let's do that, of 3 times 10, which is 30, times 13, which is 390, times 16, which is, I have no idea. No, I should. It's, I don't know. Times 25 times 60 to the 1/6 power. Oh, that's much bigger. Let's just make sure all the numbers are right. Yeah. Oh, that's huge. All right. So unless I messed something up, I don't think I did. It said raise that power, right? Yep. Oh, whoopsie. That's a big mistake. I made a big whoopsie. I was like, that doesn't seem right at all. That seems strangely huge when we're taking a sixth root. That would have been massive, and that's just not right. I didn't raise the 1/6 power. I raised the first power. So let's take the sixth root of it. There we go. 14.5. Okay, something definitely looked off. 14.517, blah, blah, blah. So 14.5. Now, which one is bigger? Arithmetic mean. Mean bigger. Now, does that mean it's always bigger? I don't know. I tried it. They just said compare it. So they did, and I compared it. The arithmetic mean was bigger. I don't know what else to say. Sometimes these problems kind of throw me in for a loop. The last set of problems, though, let's do this. In exercises 51 to 56, let x be a non-negative real number, so 0 works. Determine whether the statement is always, sometimes, or never true. Justify your answer. Okay, before we do the problems, we kind of bring up always, sometimes, never. You know when you're taking a multiple choice test and, it's like if you don't know, guess C or guess B or like whatever, you have your kind of thing. And it's like, always, sometimes, never doesn't quite work that way. As in, if you don't know, guess sometimes. Actually, sometimes is the one that you should guess when you absolutely know that it's sometimes. And how do you know something is sometimes? When you have an example of sometime when it works and sometime when it doesn't. If something always works, then you probably should be able to prove it algebraically. Not just one example, but it should be all the examples, and there's none that doesn't work. And a never is the other way, as in you can provide a counterexample to not being able to get a real example. So the sometimes should be a last resort where you found an example when it does and doesn't work. I just wanted to give you that heads up. So don't assume that these are all sometimes. And this first one looks pretty straightforward. This is x to the 1/3 times 3, which is x to the first, which is indeed x. That should be an always true case for non-negative real numbers. And for negative real numbers as well, but that should be an always true case. 52, x to the 1/3 equals x to the negative third. Now we know this isn't always true because 1/3 isn't -3. In fact, if I wrote it this way, this is 1 over x cubed. These aren't the same thing. Or let's move it one step further. Like, I'm going to stick with the algebra as long as I can. Let's multiply both sides by x cubed, and now 3 is the same as 9/3. So x to the 9/3 times x to the 1/3 equals 1, or x to the 10/3 equals 1. This is another way of rewriting the same thing that we were doing. So the question for us kind of is there a case when this is true? And obviously there are a bunch of cases when it's not true, like you plug in 2. 2 to the 10/3 isn't 1. So I found an instance when it's not true. Does that mean it's never true? What about 1? 1 and -1. If I plug in -1 into here, it actually still works because -1 to the 10th power is +1. Cube root of that is 1. So this is sometimes true. This is sometimes true. And it's true in the case of 1 and -1. I don't know if they ask us to determine why the statement's always sometimes. They don't say, like, come up with your counterexamples and stuff, but it's not always true. It's not true when it equals 2. That's why this is a sometimes provision. Oh, I'm sorry, we can't use -1. It's non-negatives, non-negatives. So 1. So I got to be careful with that. Okay, number 53. X to the 1/3 equals the cube root of x. I'll just go ahead and say always in the same. In fact, did I write always for the first one? No, always. This is always. This is the property in a nutshell. This is what it is. There are no restrictions to it either. And they're just equivalent. So yeah, that's an always. Number 54, not necessarily an always. X to the 1/3 equals x cubed. Kind of one of those things like the last one. Let's treat it the same way. Let's do something to these and make it work out. What if I divide, sorry. Oh boy. What if I divide both sides by x to the 1/3 power? Just so you can see some other properties in play. Now, by crossing those out, they're not gone. That's 1. And this is x to the 9/3 over x to the 1/3. So that's x to the 8/3. So this is basically the exact same thing that we were looking at with number 52. It's not always true. You plug in 2, that's clearly not going to work. But you plug in 1, and it works again. So this is, once again, a sometimes. I have a case when it does work, doesn't work. It only, I mean, the sometimes is that one time when x is 1, but that's all it takes. That's all it takes to be a sometimes. Number 55, and it's good that we just did a problem like this beforehand to check it out. X to the 2/3 over x to the 1/3 equals cube root of x. On this side, we get to subtract 2/3 minus 1/3, and that gets us 1/3. And x to the 1/3 is the cube root of x, the same way that we saw before. This should be an always case, especially since we're talking about no. Give me a second. This was originally presented as this, though. It was originally presented as this, and the original presentation had an x that was in the denominator. Cannot divide by 0. It doesn't matter that you subtract it later and it becomes this. This is how it was presented to begin with. If I do 0 to the 2/3 over 0 to the 1/3, you get an indeterminate. So you can't do that one. This is not equivalent to 53 because of its original presentation. And I was going to state maybe negative numbers have a hiccup or an issue. I actually don't think they do. But 0 does. You cannot divide by 0. So you'll never be able to evaluate. No, I'm sorry. For 0, you won't be able to evaluate it. For other ones, it should apply. This is good, provided that x doesn't equal 0. So, sometimes. That's a sometimes case. I didn't think these would actually take as long as they do, but I have to think about them as well. And finally, number 56, last problem. X equals x to the 1/3 times x cubed. You have to be careful. You are not multiplying 1/3 and 3. You are multiplying x to the 1/3 and x cubed. And this kind of goes back to one of those problems we were talking about before, as in this is also 9/3, and you add these. So x equals x to the 10/3. Now, when is that true? Well, let's go a little further in this. I'd like to divide both sides by x. Call that x to the 3/3, if you will. And 1 equals x to 7/3. And I keep doing this so you can really picture what this looks like and say, can I plug in something in here to get 1? And the answer, once again, is 1. 2 doesn't work, another one, but 1 works here. So this is, once again, a sometimes. I guess we didn't have a never in any of these cases. I couldn't find one, at least. Okay, and that ought to do it for this one, guys. I know that ended up extending a little longer at the end, though. This is Mr. Robinson. Thank you so much for watching. We have one more section on exponential functions, which I think is a long one. There are graphs. There are a bunch. I think it's in the 70s of problems, and the lecture might take a while. So be prepared for a super-duper long one coming up next, I think. We'll see. But that'll do it for this one, guys. Mr. Robinson, thank you so much for watching. Take care. I'll see you.